Record on the computer. Great. So for the final exam, oops. Final exam. As I mentioned before, this is going to be kind of structured like an exam 4. It's not exactly cumulative, but it will cover chapter 4, chapter 5, and then Gibbs free energy. Gibbs free energy. Gibbs free energy includes things like KEQ and Q as well. Those are all kind of interconnected concepts. It will also cover all the mass flow rate equations, which are from chapter 5 and chapter 4, mostly chapter 5. Mass flow rate, and then our energy equations. So we've been working on energy equations since chapter 2. So yes, energy equation. There was a message in the chat. The conceptual questions will cover all of the chapters we have covered in class. Let me double check before I answer that. I'll double check my final. Okay, so for the conceptual questions, they cover everything throughout the class. So there is some from your memorize sheet. Which, you know, you need to know how to convert between joule and kilowatt and watt and kilojoule. Kind of those big conversions that we've done. You should also be familiar with the concepts of like conduction, convection, radiation. Just conceptually, those are fair game. So heat transfer mechanisms conceptually. And then several of the conceptual questions are from our last chapter 5 and Gibbs free energy. This is like, these are more than half of the conceptual questions. So yeah, those seem to be kind of more, there's not going to be any that are like really, really specific detailed questions to like chapter 3. They're going to be like conceptual questions that I expect you to know. Like, you know, things about mass flow rate, things about laws of thermodynamics, things about heat transfer mechanisms, things about your memorized sheet, things about energy equations, things from chapter 5 and related to Gibbs free energy. You know, can a reaction be spontaneous and endothermic? You know, questions kind of like that from Gibbs free energy. Okay. So you should understand simple unsteady flow devices. Like unsteady flow problems. We worked a couple, there's some from chapter 5. The first half of chapter 5 was all dealing with steady flow devices, which you should know how to work these problems. And then just know some of the basic concepts and how to work some of the simple unsteady flow problems that we worked. You should be very, very familiar with using the property tables, both conceptually and in problems. You should know how to use the generalized compressibility chart. Simple meaning that we only worked like 2 unsteady flow device problems. And so you don't need to know how to work like all of the unsteady flow device problems. And you don't need to kind of know everything from that chapter. Really only focus on the ones that I went over and the ones that we talked about, where you're making that initial, assumption about uniform flow and kind of what is the difference between a steady and unsteady flow device, like just kind of simple unsteady flow devices. So like a pipe or something, nothing that's really complex with like these dynamic flow systems. The generalized compressibility chart, I already put memorized, equation sheets, property tables, energy equations. Okay, so yeah, this is all that I have written in terms of like what's going to be covered. If you remember, chapter 5 was focused on steady and unsteady flow devices and the energy and mass balance equations for these. Chapter 4 was really focused more on using the property tables and looking at closed systems. So chapter 5 was looking at open systems, steady and unsteady devices. Chapter 4 was looking at closed systems. So make sure that you are comfortable kind of going all the way back to chapter 4, which was a little simpler than chapter 5, and just making sure that you still are comfortable with that. And yeah, so as I mentioned, there are 7 conceptual questions that should be pretty quick. And then there are 4 like problem questions. I finished the equation sheet this morning, so I'm going to be posting it. It's the same as chapter 3, but I've added some of the Gibbs free energy equations. So I'll post that today, right after class. And any questions about anything before I start going over some problems that we're working?
I don't know if somebody already asked, but do you know when the exam 3, I think 3 scores will be out? Because I know like there were a couple people that hadn't taken it yet, so you can let us know.
Yeah, so I did all of the makeups as of yesterday. And so everybody has made up. I just now need to grade it. And so hopefully, today or tomorrow, I should have all the grades posted at the latest, probably Friday.
Okay, thank you.
Yeah. Other questions? Other questions? Okay. Then I will start working some example problems. So this example is from the back of your book. It is example 539. So it's from chapter 5. And it is about a diffuser, which is a steady flow device. So if you remember, there's turbines, diffusers, throttling valves, pump and or pipe and duct flow, I already said turbines, nozzles, compressors, the steady flow devices from chapter 5. So this one is a diffuser, which means that it's a steady flow device. So air at 80 kilopascal, 27 degrees Celsius and 220 meters per second, 27 degrees Celsius and 220 meters per second, enters a diffuser at a rate of 2.5 kilograms per second, enters a diffuser at a rate of 2.5 kilograms per second and leaves at 42 degrees Celsius. And leaves at 42 degrees Celsius. The exit area of the diffuser is 400 centimeters. The exit area of the diffuser is 400 centimeters squared. The air is estimated to lose heat at a rate of 18 kilojoules per second. The air is estimated to lose heat at a rate of 18 kilojoules per second. Determine A, the exit velocity. The exit velocity, and B, the exit pressure. The exit pressure of the air. Okay. So air at 80 kilopascals, 27 degrees Celsius, and 220 meters per second enters a diffuser at a rate of 2.5 kilograms per second and leaves at 42 degrees Celsius. The exit area of the diffuser is 400 centimeters squared. The air is estimated to lose heat at a rate of 18 kilojoules per second. Determine the velocity and the exit pressure of the air. All right, so first we have a diffuser. So we know that this is a steady flow device. We can approximate the air that is flowing through this diffuser to be at a steady state. We also know that for diffusers, we have no change in potential energy. We have no real work that's being done, unlike a turbine or a compressor. There's no shaft in here. There's no like work that's being put in or pulled out. The only purpose of a diffuser is to change the velocity of the air. So we know that if this is 0.1 and this is 0.2, we know that the velocity at 0.2 is much smaller than the velocity at 0.1. That's the purpose of a diffuser. So we know for sure there is a kinetic energy change because for nozzles and diffusers, that is their function, to change the kinetic energy, to change the velocity of the fluid flowing through it. Okay, we know that the temperature entering the diffuser is 27 degrees Celsius. We know that the pressure entering is 80 kilopascal. And we know that it's entering at a velocity of 220 meters per second and a mass flow rate of 2.5 kilojoules per second. We know that it leaves at 42 degrees Celsius. And we know that there is heat loss, so a Q coming out at a rate of 18 kilojoules per second. I'm gonna write these better. So we have heat that's coming out at 18 kilojoules per second. The air is estimated to lose heat at a rate of 18 kilojoules per second. Determine the exit velocity. So we want to figure out what this velocity is here, and we want to figure out what this pressure is here for our diffuser. Okay, so I'm gonna let you think for like 30 seconds about how you would start this problem. Where are you gonna find the exit velocity? We're gonna solve for that one first. Like, how are you gonna start this problem? Because that a lot of times is the hardest part for people. So take like 30 seconds, think about how you would start, and then I'll start it. Check yourself, see if you're on the same page. Good job. All right, so we have some hints about how to start this problem. The problems in chapter 5 are some of the more complicated ones that we've done, but they all start the same way, especially for steady state problems, but even for unsteady state problems, you're always going to start with your mass flow rate equations and then your energy equations. So I always start with the mass flow rate equation, right, where we have our mass flow rate of our system is equal to our mass flow rate in minus our mass flow rate out. Since this is a steady flow device and we can assume steady state system, our mass change in the system is 0. There's no accumulation. This should be very familiar based on fundies and engineering to you. There's no accumulation of mass. Our mass flow rate coming in has to equal our mass flow rate going out. And the nomenclature that I've chosen for this problem, that would be M1 is equal to M2. So this is our first step, our mass flow rate equation. Our second step is our energy equations, where we have the same type of problem mirrored, where we have our change in energy of our system over time is equal to our energy in over time minus our energy out over time. And I'm using per time because I already have some hint here that I have a per time component. Diffusers are also going to be typically including a velocity change, which has a per time component. But you can write these equations with or without this rate symbol, and they're going to be still true. So we have our energy equation. Once again, we're still a steady state system. We're not going to have any change in energy over time because we're at a steady state. So we're at kind of this uniform, steady flow. Our energy is not going to be dynamic. Our mass is not going to be accumulating. We have our energy coming in is equal to our energy going out. And then now we can expand this into our big equation of Q in plus work in plus the summation incoming of our mass flow rate times our fluid flow energy is equal to our heat out plus our work out plus the summation of our outgoing mass flow rate times our fluid flow energy. All right, for this problem, I know that I have Q coming out, but I don't have any Q coming in. And I'm assuming that there's no work for a diffuser. For diffusers and, reread chapter 5 if this is not super familiar to you, but for diffusers and nozzles, their purpose is to change the velocity, and we don't have any work. For turbines and compressors, their purpose is to generate work or compress something. So they have shafts, and we're assuming that there's no real kinetic change there. So these we draw them similarly. They're kind of similar in like design sometimes, but they have totally different purposes. So I know that I have no work that's really associated with a diffuser. It's just diffusing the air. And then from this fluid flow term, I know that I have no potential energy. So this fluid flow is going to reduce just to my internal energy, my fluid flow pressure times volume, and my kinetic energy term. So I'm going to have my mass flow rate times my kinetic energy term. So 1/2 velocity 1 squared. This is my kinetic energy term for incoming, my mass incoming. I just did a little shortcut that you can do if you want to, you don't have to. I know from my mass balance equation up here, my mass flow rates are the same. So you can just start writing them as mass flow rate. It's not wrong for you to still denote this as M1, but it doesn't matter if you don't because all of our mass flow rates are the same here. So I already kind of dropped it. Even though technically this should be, mass incoming times kinetic energy term plus our potential energy plus our pressure at point one times our specific volume because I'm working in per mass unit here. And this would be from our incoming side. And then on our outgoing side, we have heat coming out plus our mass flow rate at outgoing at 0.2 times 1/2 our velocity at 0.2 plus our internal energy at 0.2 plus our pressure at 0.2 times specific volume. All right, for this problem, I don't know pressure at 0.2. I'm not going to solve for this until part B. So that's a clear hint right now that I'm going to need to convert this into enthalpy. It was also very common in chapter 5 to convert this into enthalpy for most of the problems, unless you were given information about internal energy or you had pressure and volume terms for both sides. But we have a clue here that we don't have this pressure term, and we can't really look it up quite yet anyway. It's not like we could just use a property table. Number one, we're working with air. Maybe we could do the ideal gas law, but just looking at the problem, like we're not figuring out the exit pressure until later. That's kind of a big hint that, how else could you work this problem? What else could you condense this down into? So our equation becomes our mass flow rate at 0.1 times our kinetic energy term of 1/2 velocity of 0.1 squared plus our enthalpy at 0.1 is equal to heat coming out plus our mass flow rate times our kinetic energy at 0.2, 1/2 velocity squared 2 plus our enthalpy at 0.2. All right, so I'm going to move on to the next page. I have more work. We can change this equation to, okay, so we have mass flow rate. I'm just going to rewrite it up here. 1/2 V1 squared plus H1 is equal to Q out plus M 1/2 V2 squared plus H2. So I can rearrange this to group my velocity terms together and to group my enthalpy terms together. So I'm going to move this entire unit to this side and then factor out my velocities and then factor out my enthalpies. And, you can get our mass flow rate times our change in velocity squared over 2, 1/2 minus our mass flow rate times our change in enthalpy is equal to Q out. And we can do this because our mass flow rate at 0.1 equals our mass flow rate at 0.2 is equal to our mass flow rate. That's why we can factor the same mass flow rate out and then recombine them because it's the same mass flow rate. If I look at my problem now, I can estimate, well, I'm given my mass flow rate. I know my mass flow rate. My velocity, I am given a velocity here, 220 meters per second. And an assumption that I make about diffusers is that my velocity coming out is so much smaller, it's pretty much zero relative. That's the point of a diffuser, is to take a really large velocity and make it almost negligible. So we can assume that this entire change in velocity is our velocity of 220 meters per second. We're essentially taking all of the velocity out of this air. We're diffusing it until it's just kind of like stagnant-ish air. That's the point of the diffuser. So we can assume that our change in velocity, we know. We're given Q out. So the only thing that we don't have in this problem is enthalpy. And one thing that I noticed confused some people on the exam is sometimes you can go and look up enthalpy in the back of the property table. Sometimes you should convert it into MC delta T or like MCP delta T. And it takes practice to get comfortable with doing these. I don't think there's any like set rule. One of the things that makes it kind of obvious for this problem is we don't have two conditions for the outgoing air. We only have temperature. We don't also have pressure, so we can't confirm that we can use a property table, but also it's air. So air is not in our water property tables, and we would need to use something like ideal gas law to figure out pressure and then try to back out like in the tables in the back of the book, how we could figure out enthalpy. So this problem has two hints. The first one is that this is air, so you're probably not going to use your refrigerant and water coffee property tables. And the second hint is we don't have enough points at point 2 to fix our enthalpy at point 2. So we can kind of make an assumption here, especially if you're given in a problem statement, something like this is the specific heat for these. You can kind of assume that maybe it would be easier to go with specific heat here. So we can convert this into specific heat at a constant pressure, delta T. So our equation becomes okay, so the question in the chat, I'm confused because we're solving for V2. Why do we put it on the left instead of isolating it? Oh, you can still isolate it. I'm just trying to get everything. You can do whatever works for you. If it works better for you to isolate V2 right now and then plug in what you know. I'm just checking that I know everything in my equation before I isolate V2. So you should get the same exact answer. Yeah. So I know I have my mass flow rate times my change in specific volume. I'm my change in velocity squared minus mass, and then Cp delta T is equal to Q out. And I can look this up. I know my change in temperature. I'm given it 27 degrees to 42 degrees. I know my Cp of air, or I can look it up in the table, or it will probably be given to you in the problem statement, which it was on the last exam. I know my mass flow rates, and then this is what I'm, oh, yeah, you're right.
I'm confused. If we're solving for velocity, why
Yeah, you're right. Yeah, for this problem, you're not assuming that it's 0 because it's asking for you to figure out the exit velocity. So we know that it's going to be much smaller than V1, but I guess we're not assuming that it's 0. For some of the diffusion problems, you assume that it's 0. So I was working it without looking at the solution, which is my bad. So we're going to isolate for V2. So if we move this to this side, divide by volume, subtract our velocity 1, we have V2 is equal to the square root of V1 minus 2 Cp delta T minus 2Q out over mass flow rate. So we have our square root of 220. Sorry, this is squared, right? These are squared. Okay, so 220 meters per second squared minus 2 times our Cp of air. You can find, this will be given to you on the problem statement in the exam, but for homeworks and stuff, you need to look it up in the back of the book. It's about 1 joule per kilogram Kelvin. So we have 2 times 1.005 joules per kilogram Kelvin times by our temperature change, which was 42 degrees and 27 degrees Celsius. So 42 minus 27 is what, 15? degrees Celsius. If we had these in Kelvin, it would be the exact same difference. So this is, okay, so if we had these in Kelvin, this would be 315 minus 300, which would be 15 Kelvin. So the differences are the same. So this is 15 Kelvin. And then I have, oh God, I can't read my, let me look this up at the book. What I'm double checking is this joules or kilojoules? If you look up in table 1, are these units joules or kilojoules? Kilojoules. Okay, so this is kilojoules. This is on page 899 in table A2. Okay. So this is kilojoules times 15 Kelvin, and then minus 2 Q out over M. Our Q out is 18 kilojoules. So minus 2 times Q out 18 kilojoules per second divided by a mass flow rate of 2.5 kilojoules per second. All right. When we look at our units, here we're going to have kilojoules per kilogram. Here we have meters squared per second. Here we have kilojoules per kilogram. So we're going to need to convert these kilojoules per kilogram into meters per second. And one way that we can do this, of course, I didn't actually do this in my problem. So let me think about this. All right, so if we have,
I think it works out to, if you multiply it by 1,000, you get to the joules per,
right.
for the meter squared per second squared. I think it's 1,000.
Yeah, it is 1,000 because a kilojoule is 1,000 joules, and a joule is a kilogram meter squared per second squared, right? So in order for us to convert between our joule per kilogram meter squared per second squared, especially if this is kilojoules, it would be a 1 to 1,000 conversion. So we need to convert these two into meters squared per second squared, or convert this one into kilojoules, or kilojoules per kilogram, but that's not our unit that we want here. So we're going to need to convert all of these into meters squared per second squared, which means we're going to need to do 220 meters squared minus 2 times 1,000 and 1.05. Kilojoules. Golly, I can't write anything right now. Kilojoules, kilogram Kelvin times 15 Kelvin times 1,000 joules per kilogram per meter squared per second squared minus 2 times 18 kilojoules per second divided by 2.5 kilojoules per second times 1000 joules per kilogram meter squared second squared. All right, and then when you plug this in, you get 62 meters per second. I'm pretty sure that's what I'm getting at least, which makes sense because it's much smaller than 220 meters per second. And I'm pretty sure this is the answer that they tell you in the book too. Yes, so 62 meters per second is the answer the book gets as well. So great, I did it right. All right. For this problem, I would give you your CP of air like I did on exam 3, but this type of conversion here, you should be able to do yourself. This is something that you should have had memorized. All right, the second part of this problem asks for the exit pressure. So we found this velocity here of 62 meters per second. And then we want to figure out this pressure at point 2. So for part B, we want to figure out our outlet pressure, or our P2. And let's look at some of the information that we now know. So we know our velocities. We know our mass flow rate. We know temperature. It's air, so we can figure out density. So we probably already know enough to just find the equation that matches our what we're looking for. So I'll give you like 10 seconds to think about what equation we should start with for this. So think.
I guess.
Yep. Yeah, so we would need to use the ideal gas law. So we have our basic mass balance equations that we can go through. One of them is this density at point 2 times the velocity, or the volumetric flow rate at point 2. And we could also do the density at point 2 times the area and the average velocity at point 2. Cross-sectional area, average velocity. These are kind of the same equation. So this is along the right track, but we need to figure out how we can put in pressure here as well. And so the way that we could get pressure is through this density term. So we could convert our mass flow rate into pressure at point 2 over RT times the area times the velocity. And if we rearrange this to isolate for this pressure term, this looks a lot like the ideal gas law divided by our volumetric flow rate, which would just be our mass flow rate times RT divided by our area and our average velocity. So we know our mass flow rate. We can look up our gas constant. We're given temperature at point 2. We are given our exit velocity of 400 centimeters squared. And then we solved for this in part A. So we have everything that we need to solve this problem. When we look up the fact that our gas law constant for air is 287 joules per kilogram Kelvin. This is from table A1, but on the exam, I would just give it to you. So we can plug in 2.5 kilojoules per second times 287 joules per kilogram Kelvin times our temperature in Kelvin, which is 42 plus 273 Kelvin, which is 315, divided by 400 centimeters squared. But we want to convert centimeters into meters. So we're going to have 1 centimeter is, no, sorry, that's not right. 1 meter is 100 centimeters squared times our velocity from point A, which is 62 meters per second. When we work this out, we would get the kelvins to cancel, the kilograms to cancel here. This gives us joules per second. This would give us, yeah. So this gives us centimeter or meters squared, and then we have meters per second. So this would give us units of what, joules per second over meters cubed per second, which would be joules meters cubed per second squared. Which let me double check this.
The second should be canceled, not squared.
Oh, you're right. You're right. Yeah. So the seconds canceled. So it's joules per cubic meter. So in energy per area, which seems like a good, oh yeah, okay.
It's energy per volume.
So I'm trying to figure out. Trying to figure out if Pascal or kilopascal is a joule per cubic meter. Obviously, I've Googled this before. Okay, so one Pascal is 1 joule per cubic meter. Is that right? Pascal's not my favorite one. Joule per cubic meter. It's pressure. Okay, so yeah, a joule per cubic meter is 1 Pascal. Yeah, all right. Oof, golly. Okay, so 1 joule per cubic meter is equal to 1 Pascal. So therefore, when we get our answer here, which gives us 91,100 Pascal or joule per cubic meter, then this is also 91.1 kilopascal. On an exam, if I don't tell you what units you have to provide, you could give any of these, Pascal, joule per cubic meter, or kilopascal, as long as the units are like, they still make sense for what you're answering, right? So you could give me joule or kilojoule. If you can give me joule per second or watt, like unless I specifically tell you what unit to give me, you can give me whatever unit that you work out in the problem. All right, let me check the chat because I see stuff coming up. Okay. Oh, yeah. So remember that specific volume is volume over mass and density is mass over volume. So specific volume and density are related inversely. So what Kat said, where your density is just 1 over your specific volume. And then you can plug that in. And it looks like you got it figured out. Are there any questions still about that? Okay. Yeah, so then remember, PV equals MRT, or P specific volume equals RT specific volume is equal to RT over P, or 1 over specific volume is equal to P over RT for here. I definitely skipped right over that. Any questions? I'll make a note in my notes to not skip over that. Thank you, Kat. Okay. Then I'm going to do another problem. This problem is from chapter 4. This is 4-31. A rigid 10-liter vessel initially contains a mixture. A rigid 10-liter vessel, initially contains a mixture of liquid water and vapor at 100 degrees Celsius with 12.3% quality. At 100 degrees Celsius and 12.3% quality. The mixture is then heated until 150 degrees Celsius. The mixture is then heated until 150 degrees Celsius. Calculate the heat transfer required. Calculate the heat transfer required. All right, so we have some sort of rigid closed tank, which is indicative of chapter 3 and 4. It is 10 liters. It contains water at a mixture. And it is initially at 100 degrees Celsius. And then it is heated up to 150 degrees Celsius. We know that because of this heating up, we're going to have some heat transfer coming in. And we know that we are a mixture because A, it tells you mixture, but also we have a quality of 12.3%. We want to calculate this heat transfer that's required to heat up this mixture to 150 degrees Celsius. And we know that this is a closed system, which means we're not going to do any mass balance. No mass balance. That's chapter 5, where we start with our mass balance equations, because this is closed. This is a rigid vessel. There's no mass that's coming in. It's already there. So really how we start these problems is starting with our energy equations. The change in energy of our system is equal to energy in minus energy out. But the difference with chapter 3 was we don't have any flowing fluid. So we're really only concerned about our energy equation without fluid flow, with fluid energy, but not fluid flow energy, because we don't have anything coming in and coming out like we did in chapter 5. There's no flowing fluid, right? It's just in a vessel. So our energy equation becomes our, well, we can still assume that we're not having any change in energy of the system because this is not a dynamic system, and we're assuming that there's not going to be any energy change of our system. This is more in unsteady flow systems. So we're still going to have our energy in has to be equal to our energy out. But instead of having these energy equations include fluid flow this time, they were really still pretty simply our Q in plus our work in plus the summation of the mass coming in times our specific energy equation is equal to Q out minus W out plus, or I'm sorry, plus W out plus the summation of the outgoing mass times our specific energy equation. We are assuming there's no work being done because there's no piston, there's no moving boundary, and we're assuming that there's no heat coming out because we are trying to heat this up, and we're not told this is adiabatic, but we're assuming that we're really only putting heat in, and we're not going to be losing an appreciable amount of heat. I would probably add the word adiabatic here. Or like assume no heat loss or something to make it more clear that there's no heat coming out, but that's an assumption that we're making here.
Question.
Yeah.
Since this is a closed system, are we also assuming in this case that we're not losing energy in this point? Like there would be no ME out, or is just heat and work?
Oh, I get what you're saying. We're assuming that the overall energy of the system has to be the same, but we could still have energy that is coming in the form of like changing our internal energy, which we have. So we still have these. Okay, so for these problems, we're assuming that there's no change in kinetic and there's no change in potential, but there is a change in internal. So these equations will reduce down to internal energy, which we do have. We have a change in internal energy from this starting 100 degrees Celsius to the ending 150 degrees. But these terms, they include the fluid energy, but they don't include fluid flowing energy. So this is still like a relevant like term. It's just kind of more simplistic because it's a closed system.
Thank you.
Yeah. So since we're assuming no kinetic or potential energy here, but we are going to have an internal energy change because we're heating up this mixture, this would become Qn is equal to our, here, I won't skip this step. Okay, so Qn plus mass times internal energy 1 is equal to our mass times internal energy 2. And then if I bring this mu over, I get Qn is equal to our mass times our change in internal energy, U2 minus U1. Okay. So I have my internal energy that I'm gonna need to figure out somewhere. Mass, I'm not given any information about mass, but I am given information about volume. And then I am trying to solve for my Qn. So I'm actually gonna write this here to give me more room. We can use quality to get mass, but we don't necessarily do that first. I guess maybe you could. I didn't work it that way. But the first thing that I did was go to the property tables and try to get as much information about my starting condition and my ending condition as I could. And I know that I have a saturated liquid vapor because I'm told I have a mixture. So this is saturated liquid vapor. I'm told that it's water. So I know it's saturated liquid vapor of water. And you could go the way of getting mass first. What I did was internal energy first and then get mass second, but I don't think it really matters. What I did was I went to table A4 and A5 in the back of the book, which are our water tables. So at table A4, when you have your starting condition of 100 degrees Celsius and a quality, so you know it's a saturated liquid vapor of 12% or 0.123, which tells you that you're a saturated liquid vapor, which means you're the subscript Fg. You can look this up and we have some things that we can find here. So the first being our internal energy of our saturated liquid would be 419.06 kilograms per kilojoule using this temperature line in my saturated liquid vapor tables. And then my internal energy for my liquid vapor mixture, U sub Fg, is 2087 kilojoules per kilogram. Sorry, I switched these. Kilojoules per kilogram. I also can find my internal energy. Nope, these are my internal energies, my specific volume of my saturated liquid as 0.001043 cubic meter per kilogram, and my specific volume of my saturated liquid vapor region as 1.67 2 cubic meters per kilogram. I could also find my enthalpy, but that hasn't really come up in my problem at all, and I don't really know how helpful it would be. I could also find entropy, but once again, it's not really in my problem. So I think that this is where I would stop for my finding information about my starting condition. For my ending condition, I would look up the same thing, but at 150 degrees Celsius, but I'm still told that I'm a mixture. So I don't need to go to a different table. I can stay in the same table and just move from 100 degrees to 150 degrees. Sorry, I didn't write down one of the volumes that I need, so. But the thing about my, oh yeah, okay. Okay, so I can go to the same table, table A4. And this time I'm at a T2 of 150 degrees Celsius. And I know that I'm still a mixture. That's what it tells me. The mixture is heated until 150 degrees. And so I'm still a saturated liquid vapor mixture. So I can look up my specific internal energy of 631.66 kilojoules per kilogram. And my specific internal energy of my liquid vapor of 1,927.4 kilojoules per kilogram. I could also look up my specific volumes for this time condition, but the thing is, my container is a rigid vessel, so you really only need to fix it with the specific volume at one point, because your specific volume at 0.2 should be equal to your specific volume at 0.1. And so it doesn't really help you to look it up again, because you aren't going to use these values anyway. You're just going to say whatever I came up with here, that's my specific volume at 0.2, because I'm a closed rigid container. I'm not adding mass. I'm not changing volume. My specific volume is the same. So while you could look up your specific volumes here, you're not going to use the values, so it is not particularly helpful. Okay. Hold on. I'm second guessing what I actually did. Okay. This is true, but I'm still going to write down the specific volumes here for another reason. So the specific volume of my saturated liquid at this point is 0.001091 cubic meter per kilogram, and my specific volume for my saturated liquid vapor is 0.39248 cubic meters per kilogram. And while this is true, this might be useful. It is useful for looking at quality later. So I'm just going to write them down. Okay. So I've looked up everything that could possibly be useful from the property tables. I'm asked to find the heat transfer required. So in order to do this, I need to find both mass and my internal energies. I looked up my internal energies here, and I looked up my internal energies here. But the thing is this is for if I was all liquid, and this is for my entire liquid vapor region. So I need to use my quality relationships to find my specific internal energies for each of these conditions. So for my internal energy at 0.1, this is going to be my internal energy of my saturated liquid at 0.1 plus my quality times my internal energy of my liquid vapor region at 0.1. And for the same thing, my internal energy at 0.2 is going to be my internal energy of my saturated liquid at 0.2 plus my quality times my internal energy of my liquid vapor region at 0.2. And then I can plug these in. So 419.06 plus 0.123 times 2087. These are all going to be in kilojoules per kilogram. And my internal energy at 0.1 is going to equal 675.761 kilojoules per kilogram as my internal energy at 0.1. My internal energy at 0.2, I don't know my quality, so I can't plug that in yet. So in order to find my quality, I would need to use my specific volumes here to solve for quality. So I would have my internal energy of my saturated liquid at 0.2, which is 631.66 kilojoules per kilogram, plus for my quality equation, my quality is equal to my specific volume at 0.2 minus my specific volume of my saturated liquid over my specific volume of my liquid vapor. And this would be times 0.39248 cubic meters per kilogram. I'm going to move to the second page. Okay, so my U1 I know is 675.761 cubic meters per kilogram. My U2 I just plugged in to be 631.66. Yeah, I was rewriting it, but I can go back. Okay. Okay, so 631.66 kilojoules per kilogram plus my quality term, which is going to be my specific volume at 0.2 minus the specific volume of my saturated liquid over the specific volume of my gas minus the specific volume of my liquid, because this is my specific volume of my saturated liquid vapor, times by my U sub Fg of 1927.4 kilojoules per kilogram. Okay, so then when I plug in my, when I need to plug in my specific volume of my saturated liquid, I looked those up in my saturated vapor, but I don't have my specific volume at 0.2 yet. So I need to figure out how I can get this value. And the way that I can get this value is by using the equation, my specific volume at 0.1 has to equal my specific volume at 0.2. So then I can go back and look at my specific volume at 0.1, which I don't know, but I can use, but I have quality here, so I can solve for it. So my specific volume at 0.1, because this is V sub FG. Remember the number on the end too. Oh, did I write a different number on the end? Oh, I wrote specific volume here, but this should not be specific volume. This is our U sub FG, 1927.4 kilojoules per kilogram. So this should be UF, this should be UFG. These are quality. So UF, UFG, solving for quality. All right, so our specific volume at 0.1 is our specific volume of our fluid at 0.1 plus our quality times our specific volume of our saturated liquid vapor at 0.1. That says 2, but I meant 1. Which is 0.001043 plus 0.123 times 1.6720 cubic meter per kilogram, which then gives me 0.20657 cubic meter per kilogram as my specific volume at 0.1, which equals my specific volume at 0.2. And now I can plug into here. So my U2 is going to be equal to 631.66 kilojoules per kilogram plus my specific volume at 0.2, which is 0.20657 cubic meter per kilogram, minus my specific volume 0.2 of my saturated liquid, which is 0.001091 cubic meter per kilogram, over my saturated liquid vapor specific volumes, which would be 0.39248 cubic meter per kilogram, minus my specific volume of my saturated liquid, 0.001091 cubic meter per kilogram, times my U sub FG of 1927.4 kilojoules per kilogram. Whew. So then my U2 becomes 1,643.53 kilojoules per kilogram as my U2. I have my U1, I have my U2. I have almost everything I need to solve except for mass. So the way that I can get mass is by doing my volume divided by my specific volume. I know my volume at 0.1 to be 10 liters in the problem statement, and I know my specific volume at 0.1 to be what we figured out here, 0.20657 cubic meters per kilogram. But now I don't have cubic meters and I don't have the same units, so I need to convert my cubic meters to liters. So 1 cubic meter is 1,000 liters. So this would be 0.1 cubic meters divided by 0.20657 cubic meters per kilogram gives me, finally, sorry, I know we're out of time. I'm trying to hustle. 0.0484 kilojoules as our mass. So now we have everything we need to plug in to our equation, which was our heat transfer was our mass times our change in internal energy, which is 0.0484 kilojoules times U2 minus U1, which is going to be 1,643.53 minus 1, which is 675.61 kilojoules per kilogram. which gives us kilojoules as our unit. That makes sense because that's a unit of heat transfer. This is 46.84 kilojoules as our answer. Okay. Whew. So I picked this problem because a lot of you on the last exam just plugged in these values to your equation and you forgot that it's a mixture. So this value isn't your value. You have to incorporate these quality equations. And so I thought this problem used more quality equations than any problem I've ever seen before because you have to use it like 3 different times. So I think that this one is a nice one to practice to make sure you're understanding how to use the quality problems. This is problem 4-31 in your textbook. So you can work it again yourself. But the hardest part about this is just using these qualities, right? It's really easy to look these up in the table. It's easy to do this basic energy equation. The hardest part is getting your qualities sorted out correctly. So it's all this busy work here. Okay, the last problem that I had, which I didn't get to, was just another Gibbs free energy problem, but I feel like we've practiced that a lot lately. I think it might have been better to spend your time focusing on chapter 4 and chapter 5, which we haven't done for a few weeks now. So one of the other things that I think is really important from this class overall are your mass relationships. Not only mass flow rate, but also how they relate to specific mass, you know, the ideal gas law, all of these things, how you can kind of manipulate these basic equations that you're supposed to know. So I know we're over time, but I guess technically not really, but what questions are outstanding? What sort of questions do you have? Okay, well, we haven't done chapter 4 for several weeks now, and it can be kind of confusing with chapter 5. So I would really emphasize, you know, Gibbs free energy should still be pretty fresh. We've done that a lot. Going back and really getting chapter 4 closed systems, chapter 5 open systems solidified would be a good use of your time. If you're taking the exam this Friday, please be there by 11:30 in our normal classroom with a calculator and a pencil. I'm posting the equation sheet right now after class on Canvas. And if you're not taking the exam this Friday, please use it to study and then show up Saturday at 10 a.m. in our classroom on May 1st. Email me if you have any questions or concerns. And yeah, any questions? Okay, well, if I don't really get a chance to talk to you again because we're doing exams, I hope you enjoyed thermodynamics this semester. I apologize. I make a lot of little mistakes, and it's because I am a microbiology person. I am not particularly strong at thermodynamics, so I have to teach myself this stuff before I teach it to you. So I hope that you had a good experience and that you liked me and you liked the class. And, you know, I had a good semester even though we were online. So, you know, I hope you take away some interesting things you learned from Thermo. It helps for the FE. And yeah, thanks for being my student and thanks for a great semester. So thank you. Yes, I thought it was a very respectful, happy environment. So I appreciate it. All right, I will see you on Friday or in a couple of Saturdays from now. Good luck studying. Email me with any questions and I'll see you all later.
Have a good week. Thank you.
Thank you, you too. Good luck with everything. I know it's busy.